So we just carry this down, it has a what? A dx, carry this down, it's got a what? And you should notice everything is now in terms of x, which it is. And you got a simple integral. This will give you the exact area. I just felt we got a nice problem up here, we might as well find the exact answer right away. We'll do a few more Riemann sums. Let's integrate 8x cubed. 2x. Oh good, 8x to the 4th over 4 is 2x to the 4th. That's 2 times 4 to the 4th. That's 2. That's 64 times 4. So what's 2 times 256? That's exact. What did we get before?
448.
448, you know, close. Underestimate though, if you all agree. It was an underestimate. That's the exact value.
So in double integration, first you do with respect to y, then you do it that answer you do integrate with respect to x.
Right.
Okay.
That's what we do. On you do everything with respect to y, and everything with respect to x. Now, we could have set up this problem as dx dy. We would have started out by integrating everything with respect to the x.
Then y.
X to the 4th over 4th y. You do all that math, you'll still get the same answer. So in this problem, you had a choice. And that always happens when it's over rectangles. Dx dy, dy dx, set it up the way you want. Right? And either way, it's going to get you the problem, because one of them you're going to do it in terms of one letter before the other. Nice. Hey, before we leave Riemann sums. Before we leave Riemann sums, I want to make sure you know how to do this from a table and from contours. Because you did it from a formula, right? So when you just did Riemann sum, I always want to make sure we don't skip something. Like, okay, we did a Riemann sum from given a formula, like z equals. Can you do it from contour curves? So, I'm going to build contour curves. Does everyone have a copy of the problem set? I'm just going to give you a problem that looks like that, number 2. Just give you something similar to this. So I'm going to pretend you got some contours here. And here, 1, 2, 3, 4. Okay. Just give you something similar. Let's see, there's the x-axis, there's the y-axis. Let's say you got a contour that goes through here. I'll do something similar to this. You got a contour that's going to this point. Another one going through there. We got another one cutting through here. Let's see. Yeah. Right here. I'm just going to draw some contour curves. Now let's just say you got contours. They're just going like this. And pretend the temperatures. Geez, use different numbers. Okay, this is 3 degrees. This is 6 degrees. And that's 8 degrees. But can you estimate this? Estimate double integral 0 to 4, 0 to 4, the function of x and y. This time I'll write it as dx dy. And here's your function of x and y. Alright? This is the contour map. Function of x and y. Well, don't they have to say m and m? Come on, how about m equals 2 and n equals 2? And use the midpoint method. Well, I'm going to draw this grid again. 1, 2, 3, 4, 1, 2, 3, 4. N equals 2, split up x in terms of 2 regions. N equals 2, split up y in terms of 2 regions, right? Use the midpoint method. Okay, there, 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 and there. So when I'm going to get the estimation of double integral, how many length width heights will it be? It'll be 4 of them. Well, look at this image. This went from 0 to 4 and 0 to 4. What's the length and width of this region right here?
2 by 2.
2 by 2. This one right here?
Same.
2 by 2, 2 by 2, 2 by 2. So a bunch of 2 by 2s again. And thanks for being patient. I just wanted you to see. How do you get the heights this time? Last time you plugged it into a math formula. Now all you have is this. So how are you going to estimate the height right there? Want to see it? And you can draw the grid out when it comes to the practice set, put it right on this thing. Right, you can go 4 by 4. You can see this grid right on top of this, and by using the midpoint method, you can see the exact midpoints. What's that midpoint right there? 3. All right, how about over here?
6.
You got to follow that contour. 6. How about this one? 6. And lastly, what was this one?
8.
8. Hey, again, if you every problem on the textbook, sometimes the contour it's a little bit off from where the midpoint is, so you got to estimate. Oh, 7.8, right? Oh, okay, it's about 2.9. So if you do the problems out of the textbook, I just want to point that out. If I put it on a test, I always make it go right to the midpoint, so there's no question you have to estimate. Just to make no problem. And that'll be it, right? Add all these up, and you'll estimate that double integral. Does that make sense? You can factor up the 4, what do you get? Plus 3 plus 6 plus 6 plus 8. 23, 80, 90. Oh, again, what if you wanted to estimate the average, pretend these were temperatures, the average temperature? What do you divide out? Yeah, the whole area. Divide out the 16 area from that, you'll find the average value. Hey, and one more of these, before we do a bunch of cool double integrals. This is a table. So, you got the practice set problems? Great, if not, you just look up here on a board. Again, maybe we have to at least set this thing up. This is a swimming pool here. Let's see what we get. Can I erase this one? All right. Look at that all there. Estimate another function of x and y. Well, let's do a Riemann sum from a table. Far enough? Yeah. Okay, here's our problem, everyone. The following table shows the depth of water in a swimming pool, measured in feet. Use the midpoint rule. M equals 2, N equals 2 subdivisions. Remember, N is for X, N is for Y. To estimate the volume of water in this pool. So when I set up my grid again, I'm going to do this. X will go from 0 to 40, the Y will go from 0 to 20, right? I can do that. X goes from 10, 20, 30, 40. The Y goes from 5, 10, 15, 20. Not drawn to scale. If you want me to draw it to scale, I can, but 5, 10, 15, 20, right? Here's my rectangular region. Not drawn to scale, but I'll just make this go to 20, this goes to 40. So what would this be? 10, 20, 30, 40. This would be 5, 10, 15, 20. They said M equals 2, N equals 2, so I should split this up into what?
2 meters.
Split this into 2 regions, and N equals 2. Split that into 2 And what are we estimating? I'll set this up. Now, if I write dx dy, what are the limits for x? 0 to what?
40.
40. What's the limits for y?
0 to 20.
0 to 20. And we're just going to estimate this. And this is going to be an estimation of the volume of the swimming pool. Right? This will estimate the volume of the swimming pool. But we are just building these rectangular solids throughout that whole swimming pool, where they got the actual depth readings. So I can tell what's the length and width of this? 10 by 20.
20.
10 by 20. 10 by 20. 10 by 20, not drawing the scale. How do I get the heights again? What method did they use? Use the midpoint rule. So I'll poke midpoints. Boop, 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 boop. And how do I get these values? 2 problems ago, we got it from a formula. We plugged it in the z equal to x cubed y. The last problem, we read them off contours. Now you get them from the what? From the table. That's all. So let's do it. Help me read this. What's going on when x is 10 and y is 5? Right, the depth is 10. So I'll put a 10 here. Right, a 10. How about when x is 30, y is 5? 11? How about when x is 10, y is 15? 10, 15, 5, and... Yep. And one more. What about when x is 30 and y is 15? I get the number 4. On the table. And there you go. I can hit this thing off. We'll just estimate that. Length times width times height, right? Length with height. Length with height. 2 more length with heights. Every length and width was 20 by 10, right? 10 by 20, 10 by 20, 10 by 20, 10 by 20, but what were the 4 heights? Or in this case, water depths. We get 10, 11, 5, and 4. No particular order. I'm going to factor out that 10 times 20. All right, what's 5 plus 4 plus 10 plus 11? Is that 30? So what's 200 times 30? There you go. Now what were the units? I don't even know. You can read it. Did they give us units? It was in feet, so cubic feet. Cubic feet. That's an estimate of the volume. That's what we're doing. Hey, great job. So now everyone, what we'll do is let's talk about another double integral over a rectangular region, but let's, from here on out, no more Riemann sums. Let's get exact answers. So, how much is something like this? Zero to 1, 0 to 2. So we estimate this. I do want to point out, everyone, this is an estimate of volume, right? But with all these problems, maybe I should say net volume, because do you recall in Calc 1, integrals, couldn't integrals come out to be negative? Yes. Couldn't integrals come out to be 0? So what if this surface is dipping below the xy plane over a certain region? Yeah, now you can get like negative values applied to this. Does that make sense? Or what if half the surface was above the xy plane and the other half was below the xy plane? It can even out and get an answer of what? 0. But it looks like here, this surface, does everyone agree that's a plane? You recall in our course, that's actually a plane. So we got like a flat plane just over that rectangle region. That's what's going on here. We're estimating the volume. Estimate the volume under a ramp over the region 0 to 2, 0 to 1. So if you have 4 numbers, everyone, that's a rectangle. It's always a rectangle when you have 4 numbers. So we're gonna set this up in terms of this. I'll put nothing here first. How about that? I'll start the problem like that, because if I give numbers, I gotta tell you who's x and y. Well, what if they said this? Y goes from 2 to 0, and x goes from 1 to 0. Now you have a choice on how to set it up. But this is the region. Let's draw that. Get the volume underneath this surface over that region. That's what your volume. Find the volume under that ramp, that flat plane, over that rectangular region. So how do you want to set it up? You want to do dy dx? Good to me. Because you have an option. So if I write dy dx, what number do I put here?
The y value, right?
Good, 0 to 2. This will be
0 to 1.
0 to 1. And we're ready to rock and roll. But you could have done dx dy, you would have just done what?
Inverse it.
Switch this around. Now, because I chose this, we're doing an iterated integral. We gotta do that first. So what's the integral? Be careful. What's the integral of x plus y with respect to y?
So xy plus half y squared.
That's the hardest part. Everyone hear what he said? That was correct. The integral of x with respect to a y doesn't become like a constant 0. That was, we were thinking partial derivatives. We're now doing partial antiderivative. So the integral in x with respect to y becomes a x y. This one's easy. That's just what?
Half y squared.
But I'm worried someone would just write down the letter x. That could throw up the whole problem. Oh, and what are we plugging in here?
2 and 0.
And where are you plugging into which letter?
Y.
Into what? So I get 2x plus 2. I love zeros. You plug in 0, what do you get?